Okay, so the next video is going to look at the Clausius-Clapyron equation, which is, I wrote it out here for you, but I felt like it's just the formatting. It's the natural log of P2 over P1, so you've got two different gas pressures. When that'll be equal to the negative heat of vaporization over R, but not 0.08206 R, 8.31 R. So I'll give you the R value and I'll give you the Clausius-Clapyron equation. And then you have in parentheses the difference of the inverse of T2 minus the inverse of T1. So when you look at the way that this is set up here and the way I wrote it on the notes, this is actually what we're going to do in lab next week, where on the y-axis we're going to plot the natural log of pressure. On the x-axis we're going to have inverse of temperature. And what we'll notice is the slope of that line is going to give us our heat of vaporization, essentially. So that's going to come next week in lab. But in lecture, we are going to do one of two things. If we know the heat of vaporization and we know the pressure of the gas at a certain temperature, we can solve for the pressure at a different temperature. Or if we know the vapor pressure or gas pressure of a certain liquid or gas pressure, so vapor pressure, at two pressures at two different temperatures, or at a pressure at two different temperatures, then we can solve for the heat of vaporization. Okay, so we've got carbon disulfide, CS2, has a normal boiling point, right? So our temperature is 46 plus 273. Remember, we always got to be in Kelvin. So when I add my 273, I have 319 on my Kelvin scale. Normal means that the pressure is 1 atm or 760 torr, right? But we just remember normal meant standard pressure of 1 atm. And we have a heat of vaporization that's given to us at 26.8 kilojoules per mole. And we want to know the pressure, so P2, when our T2 is 35 degrees Celsius, and again adding the 273, so 35 plus 273 in Kelvin is 308. All right, so basically what we have is we're looking for P2, we have our P1, we have our heat of vaporization, R is a constant, and we have our two different temperatures here. Now, the textbook that I always used, it didn't have the negative here for heat of vaporization. Instead, it flipped T2 and T1. So if you did do it that way, you don't have to worry about the negative here, which is why I always did it that way. So the formula will be given, so you can just follow the formula, but I don't have to worry about the negative here. If I flip this, I go inverse of T1 minus inverse of T2. Because in my experience, for me, it was always easy to kind of just misplace a negative by mistake. So I'm going to plug everything in. I got Ln, P2 is what I'm looking for, right? We don't know what that is. The initial pressure is 1 atm, so that goes in parentheses. My heat of vaporization is 26.8 kilojoules. My R is 8.31 joules per mole Kelvin. Notice the energy unit isn't the same. So your heat of vaporization, you typically need to multiply that by 1,000 to get it into joules. All right, so that'll take care of that, joules per kilojoule. So we'll get rid of kilojoules that way. And then in this parentheses, we have 1 over, since we left this a positive, we're going to do the inverse of T1 first. So T1 was 319 Kelvin minus the inverse of T2, 308 Kelvin. All right, so first thing I'm going to do is I'm going to do this part in parentheses first. So I always love this TI-36. This was my favorite calculator. It's got the inverse key. So what I would do here is I'd say, okay, I got 319 inverse minus the 308 inverse. All right, so that difference in the parentheses is a negative 0.000111957. All right, if you write everything out like step by step, keep as many digits as possible. Because if I round this to just 0.0001, I'm going to have a very different answer at the end. All right. Next part here, I'm going to take the 26,800, right? So 26.8 times 1,000, so 26,800. Divide that by the 8.31 constant. And so that answer is 3225.030084 for my calculator. And this will be equal to ln of P2 over 1, which means just P2. Now, before I can get rid of the natural log, right, or before I can break up P2 and P1, I have to get rid of natural log. So let me go ahead and multiply these two together. So the 3,225 is still in my calculator, so I'm going to multiply that by 0.000111957 negative. So this is equal to a negative 0.361064693. And if I want to get rid of the natural log, E, right, is the inverse of natural log. So your calculator always reminds you of that, right? So on my calculator, let's see if it'll focus. I have natural log. Let me see if I can focus in here really quick. It's not letting me do it. Oh, there it is. Okay. So there's my natural log inverse, right, the E. So I'm going to hit my second function. So I got my negative 0.36. I'm going to hit second. There's my E. That gives me the answer. So this is equal to 0.69693. And that was equal to P2 over 1. So when I solve for P2, it would be 0.697 in atmospheres as my pressure. All right, so let me just walk you through the calculations again on my calculator. All right, so first thing I did, I'm going to do the inverse of 319 minus the inverse of 308. Enter. All right, that's this answer. Then I'm going to multiply by 26.8, multiply by 1,000, and then divide by 8.31 constant. So that's this answer here, negative 0.361. Now, to get rid of the natural log function, I take the E, so that's here, so I hit second E, and there's my answer. It's 0.697, rounding to 3 sig figs. And since that was equal to P2 divided by 1, I just cross-multiply the 1, I get the same answer. So that would be my pressure. So let me think if that makes sense. All right, so at T1, I'm at 319 Kelvin, pressure is 1 atmosphere. When I go to T2, I'm at a lower temperature, I've decreased temperature, so my pressure should also decrease. All right, so that makes sense. It's less than 1, that's as much as I know. All right, now, carbon disulfide, CS2, if we think about that in terms of VSEPR, it's just like carbon dioxide, right? Nonpolar molecules, so in terms of intermolecular forces, we should only have dispersion here. There's no hydrogen bonding. Overall, the molecules should be non-polar, so no dipole-dipole forces. So selenium tetrafluoride, this one is our seesaw, right? Because we've got that lone pair on the sulfur with an expanded octet. So here we should have dispersion forces and we should have dipole-dipole forces. All right, so question here says we've got a vapor pressure of 757 millimeters of mercury at 105 C and a lower 522 millimeter mercury vapor pressure at 95 degrees C. What is that heat of vaporization? Okay. So first thing I'm going to do is say, okay, I got a P1 of 757 millimeters of mercury when T1 is 105 Celsius, but of course we always add our 273 to get to Kelvin, so we really have 378 Kelvin. Our P2 is 522 millimeters of mercury when T2 is 95 degrees Celsius, or 368 Kelvin. So when I look at my formula here for the Clausius Clapyron, I've got ln of P2, 522, over P1, 757. All right, the units of pressure will cancel out. And it doesn't matter if I'm in ATM or torr or whatever, it's just the units have to cancel. And I'm solving for the heat of vaporization, that's going to be my X. Divide that by 8.31. And then I have the inverse of T1, so the inverse of 378, minus the inverse of T2, so 368. All right. So because I have my P1 and P2, I'm going to go ahead and solve here. So I'm going to take the 522, divide that by 757, and then hit the natural log key. So this answer right here gives me negative 0.371696. That'll be equal to x over 8.31, and then let me go ahead and get the temperature differential. So on my calculator, I'm going to take the inverse of 378 minus the inverse of 368, and I get negative 0.000071889. So to solve for x, I'm going to take that, I'm going to divide both sides by the 0.000071889 negative. All right, and then I'm also going to cross multiply the 8.31. And so when you get this answer, it's going to be quite large. You can divide it by 1,000 if you want to get it into kilojoules, which is typically how heats of vaporization are reported. Or you can look at it and say, okay, to 3 sig figs, this is going to be, well, it's 42,966 joules per mole. But if I divide that by 1,000 to get it into kilojoules, we'd have 43.0 kilojoules per mole. So that would be our heat of vaporization. All right. So again, on the calculator, what I did, all right, first thing I did is I took my 522 divided by the 757, right, and then I hit my natural log key. So there's the 0.371696, right? Then what I did, and you could have started over here if you wanted to, but I did that first. So I did the 378 inverse minus the 368 inverse and got my answer. That's that negative 0.000071889. Now since I'm dividing both sides by that number, I hit the inverse key again and then multiply it by 0.371696 negative. And then I'm going to cross multiply the 8.31. And so that's where I got that, 42,966. But that's in joules. Heats of vaporization are typically in kilojoules. So if I divide that by 1,000, I get my heat of vaporization, all right, as 43.0 kilojoules per mole. So if I compare that just really quick to the carbon disulfide that we had earlier, carbon disulfide heat of vaporization was 26.8. This one is 43, right? Higher heat of vaporization, higher intermolecular forces. So those two are always tied together. So higher intermolecular forces means higher boiling point, melting point, but also higher heat of vaporization, right? More energy required to convert it from a liquid to a gas phase. And basically that's what this is looking at. Like as you increase that thermal energy, what impact does that have on the gas pressure, right? Moving that into the gas phase. And so what we saw here in the last one, like a weaker vapor or a weaker heat of vaporization means less of a temperature change, more of a pressure change, right? And so here, that's what this Clausius Clapyron equation takes into account. All right, looking at increasing temperature, what happens to pressure, and how does that relate to intermolecular forces and heat of vaporization. All right, so that's the Clausius Clapyron. Now there's more phase changes. We've talked about liquid to a gas being vaporization, gas to liquid being condensation. All right, what if we melt, right? So if we go from a solid to a liquid, this is melting or fusion, right? And then if we do the opposite, right, liquid to a solid, freezing. All right, and also called solidification. So the book I always used, they actually stuck with freezing, but this one calls it solidification. So those are opposites. And again, the solid to a liquid, you're going to have to break up intermolecular forces. This is going to be endothermic. Taking a liquid to a solid, you're going to form intermolecular forces, so exothermic. So anytime you break up intermolecular forces, always an endothermic process. When you form intermolecular forces, it's going to be exothermic. All right. So that's that phase change. Then you have a direct phase change from a solid to a gas. This is called sublimation. So think of dry ice at Halloween time, right? Your carbon dioxide solid goes right into the fog, the gas phase. That sublimation process, again, breaking intermolecular forces, always endothermic. And then the opposite, the gas to a solid, this is called deposition. I think of deposits, right? So the gas molecules deposit into solids. And again, that'll be exothermic because you're forming intermolecular forces. All right, so in terms of our phase changes, we're going to look at that on a phase diagram on the next page. But this example here, imagine a container of ice being heated until all of the ice has been evaporated. So we're taking that water or ice in the solid phase, we convert it to the liquid, we melt it first, and then we convert it to a gas. So what are all the things that have to happen here? So first, you have to get the ice up to temperature to melt it, right? You have to get it first hot enough to get to that 0 degrees Celsius mark. That is a heat capacity, right? So we learned that back in thermo, that we would have to know the mass of the ice, the heat capacity of the ice, and that change in temperature to get it to 0 degrees Celsius. So that would be heat capacity, the MCAT formula. Next, we would look at that phase change. So we would know, or need to know, the heat of fusion, the delta H of fusion, to take it from a solid to a liquid. So that would be step 2, right? We need to know that heat of fusion. Then we'd have to take that liquid and go from 0 degrees Celsius to 100 degrees Celsius. So again, that's another heat capacity question. 4.18 would be the heat capacity of the water. We're going up 100 degrees Celsius from the freezing point to the boiling point, and then we would just need to know the mass of our liquid sample. So that would be the energy of that temperature change. Then from there, to take it from a liquid to a gas, we'd have to know that heat of vaporization. So there's 4 different steps that we would have to calculate there just to figure out the energy to take ice to a gas phase. Now, how would that relate to converting the water from the gas phase to the solid? It would just be the opposite, right? So first thing is the gas, you'd have to cool it to 100 degrees Celsius, right? Then you would have to take the gas to the liquid. Then for the liquid, you'd have to cool it to 0 degrees Celsius, and then you'd have to take the liquid and convert it to a solid. So in terms of all of the phase changes there, right, you have your MCAT formula for a temperature change, and then that phase transition from gas to a liquid, right, that instead of vaporization, that's condensation, and liquid to a solid, instead of fusion, that would be freezing or solidification. All right, so just the same, just in reverse, right? So instead of the going from ice to gas being endothermic, this would all be exothermic, right? Because your temperature is cooling, right? So your final minus initial would be positive. So the big difference here is that this would be all exothermic instead of endothermic like we saw. So taking ice and breaking it into a gas, breaking all those intermolecular forces, heating it up, endothermic all the way through. You've got to put energy into that. Going in the opposite direction, that would all be exothermic, right? We learned that with Hess's law. If you reverse a reaction, you're going to change the sign of the delta H. All right. Then the phase diagram that I mentioned. So phase diagram, they're different for different substances. So every substance has its unique phase diagram. So if I look at my phase diagram kind of generically, typically there's pressure and temperature, and you have like a curve, you get to a point, you get another curve, and then another curve. And what you look at here is you have the solid phase, then the liquid phase, and then the gas phase. And this point right here, this is called the triple point. because it is the point which at this temperature and this pressure, all three phases can be in equilibrium. All right. When I look at the phase changes that are occurring, right here, we're transitioning from a solid to a gas, right? That was called sublimation. All right. For this one, going from a solid to a liquid, vaporization, or sorry, fusion, melting. All right, and then liquid to a gas over here, that would be vaporization. So endothermic, right? Increasing temperature, right? Putting energy in. Endothermic step, going from solid to liquid to gas. So solid to liquid, fusion, liquid to gas, vaporization, and then solid directly to a gas, sublimation. If we reverse that, the exothermic steps are when we take a gas to a liquid to a solid, and yet I wrote gas, sorry, solid. Gas to a liquid instead of vaporization, that's condensation. Liquid to a solid, freezing or solidification. And then the opposite of sublimation, from a gas directly to a solid, deposition. All right, so just learning all of our phase changes. Now what we saw with intermolecular forces and how it relates to vaporization, the same is true for fusion and sublimation. The stronger the intermolecular forces are, the more energy it will be to change the phase. So all of the endothermic steps, the higher the intermolecular forces are with those molecules, the higher the energy requirement will be to either go through fusion, vaporization, or sublimation. So stronger intermolecular forces correspond to a larger heat of vaporization, a larger heat of fusion, or a larger heat of sublimation, higher boiling point, higher melting point, and then lower vapor pressure. That's sort of the oddball. Remember, vapor pressure is how much of it is in the gas phase and equilibrium. Well, if the intermolecular forces are really strong, there's not going to be a lot in the gas phase, right? So this is kind of key right here, sort of remembering how intermolecular forces relate to all of these different phase changes. All right, then kind of tying some things together on the next page, right? I have all of the intermolecular forces here. So dispersion, dipole-dipole, hydrogen bond are the three that we learned. Intra are the forces within the molecules, ionic bonding, covalent bonding, right? So we're looking at intermolecular, right, between the molecules. So we've got two substances. One has a boiling point of -78 degrees Celsius, the other one's 65. One of them is fluoromethane, the other one is methanol. Which is which? All right. So we have to draw our structures, right? VSEPR is important here. So we got CH3 and then F. So there's my CH3F. The next one is CH3 and then OH. All right. So what type of forces do we have here? Both of them have dispersion. So we look at our molecular weight. We got 12 plus another 3 is 15 plus 19. We're about 36 grams per mole. And then when I look at the methanol, I've got 12. Actually, let me just add it up really quick. Not 36, 34. I knew it when I said it. And then for the methanol, I've got 12 for the carbon, 16 for the oxygen, and then 4 for the hydrogen. So we're about 32 grams per mole. So molar masses are about the same. They both have dispersion. So that's not going to explain the difference in the boiling points. When I go next, I know I've got an electronegative fluorine here. So that's going to create polar. Same is true for the oxygen. That's our second most electronegative, right? So we know that there's going to be dipole-dipole forces here. Both of them are polar. So far we're not explaining why the boiling points are so different. the third force that we learned was hydrogen bonding, right? And that's what we have here with the methanol. We don't have, you have to be careful because remember we said hydrogen bonding is when the hydrogen is bonded to a nitrogen, oxygen, or fluorine. And if you looked at that molecule, you might be tempted to think that the hydrogen's bonded to the fluorine, but it's not. Hydrogen's bonded to carbon, the fluorine isn't bonded to the hydrogen. So there's no there's no hydrogen bonding here. In the methanol, we see the hydrogen bonding. So that adds to those intermolecular forces. And the hydrogen bonding, what happens is that you've got negative and positive, and that likes to line up. And hydrogen bonding, actually what happens is this electronegative oxygen will partially bond to a neighboring hydrogen. So you can see a picture of that in your book with when it looks at the hydrogen bonding. But we recognize that there will be hydrogen bonding here. And so when I look at the boiling points, the fluoromethane should have the negative 78-degree boiling point, and the methanol should have the 65-degree boiling point. All right. Same thing, let's look at the three compounds below and look at all the possible intermolecular forces. So the C4H9, so we'd have a four-membered carbon chain. It's got an alcohol group on it. There's 1, 2, 3 hydrogens, 4, 5, 6, 7, 8, 9. So those are all just hydrogens. So this is called butanol. The carbon dioxide, we saw that earlier, linear, right? No polar, just kind of straight line. The SO2, this is bent because of the lone pair on the sulfur. So I look at these, they all have dispersion, because we know that. All right, the CO2, this one is non-polar, so that's all it has is dispersion. There's no dipole-dipole, there's no hydrogen bonding. With the SO2, we expect sort of a negative end and a partial positive end, right? The oxygens are more electronegative, pulling down, nothing pulling up. So here we should have a polar molecule, dipole-dipole forces. With the butanol, we have a negative end, right? So we know that there's also going to be dipole-dipole forces here. But now we see some hydrogen bonding because of the hydrogen bonded to the oxygen. So if I'm going to guess my boiling point, if we're increasing boiling point, what we want to think about is we are increasing the intermolecular forces. So boiling point is going to increase with increasing molecular forces. So lowest boiling point should be the carbon dioxide. That has the weakest intermolecular forces. Then next in boiling point should be the SO2. And the highest boiling point should be the butanol, because this one has the highest intermolecular forces. All right, so again, kind of going with other things that we talked about in this chapter, could have been boiling point, could have been melting point. If we looked at that, it's the same idea, breaking those intermolecular forces. The other thing we could have looked at was the heat of vaporization, or the heat of fusion, or sublimation. All of those phase changes that require you to break intermolecular forces, right? Liquid to a gas, solid to a liquid, or solid to a gas. The higher the intermolecular forces, the higher that enthalpy change will be, that energy required. But if I asked you this follow-up question, which has the lowest, right? Video froze. All right, I'm going to have to pause here for a second. All right, I think I got it. Sorry. So, which has the lowest vapor pressure at 298 Kelvin? All right, so which one has the least amount in the gas phase at roughly room temperature? The lowest vapor pressure means the highest intermolecular forces. So that would be the butanol, the C4H9OH. Higher intermolecular forces means the more likely those molecules are being held together, so less likely to be in the gas phase. All right, so this one is sort of the oddball. Lowest forces means lowest boiling point, melting point, and all those enthalpy changes. Highest intermolecular forces, highest boiling point, highest heat of vaporization. But lowest vapor pressure means highest intermolecular forces. All right, so that concludes everything in Chapter 12, our last chapter.